Okay, so today we're starting Chapter 3, Lesson 1, lots of vocab words. And so we'll have our vocab sheets. I'm just going to highlight them. So we're talking about the constant rate of change. I abbreviate that the CROC, or croc, like crocodile. So if you think about a crocodile, they have bumps on the outside of their back. So we're going to kind of think of that today, remind ourselves of those crocodile bumps on the outside of the little reptile's body. So when I start talking about crocodile bumps, I want you to remember outside. This is a happy crocodile. The outside bumps. So we have some vocab words here. Relationships that have straight line graphs, like the one on the previous page that we can't see, are called linear relationships. So relationships that have straight line graphs. So as the number of songs increased on that page by 2, it was always going up by 1. So it always went up 2 songs per 1 minute, so that was always a constant rate of change. The rate of change between any 2 points in a linear relationship is the same or constant. A linear relationship has a constant rate of change. There, we'll talk about that one being the vocab word. All right, so on slide 2, I have some hints on how to find the constant rate of change. Something is linear if it forms a straight line on a graph. In order for the relationship to be linear, it has to have a CROC, or constant rate of change. So it changes by the same amount every time. How to check for the constant rate of change. Simplify all the outside. Remember, the crocodile bumps are on the outside of its body. So we're going to simplify all the outside ratios, typo, on a chart. If they are the same, it has a constant rate of change, aka meaning it's linear. On a graph, we're going to use either easy points to simplify, but if it makes a line, a straight line on a graph, you know it's linear. Lines can create a positive constant rate of change, so that's up and to the right. So positive is like this, and negative can go down, so it's down and to the left. That would be a negative constant rate of change. Okay, so a couple slides here where we're going to check for the constant rate of change. Slide 3 says the balance in an account after several transactions is shown. Is the relationship between the balance and the number of transactions linear? Balance and number of transactions linear. If so, find the constant rate of change. If not, explain your reasoning. So we're going to do our crocodile bumps on the outside. And then from 170 to 140 is a decrease of 30. We're going to check all of these. Again, a decrease of 30 and a decrease of 30. Now this is going up by 3 each time. So we're going to set up a ratio, and all of these numbers are the same. So we only have to check one of them and simplify it. So the balance is negative 30 over 3, because it says number of transactions second. So the constant rate of change would be negative $15 per transaction. They're losing money. So the constant rate of change is negative 15. And then if we ever have to explain it, that would be put a label on it, basically. So if they're just asking for the constant rate of change, it's negative 15. Or if they're just asking is it linear? Is it linear? Yes, because the constant rate of change is negative 15. Okay, so another chart here. So we have our crocodile bumps. These ones are 5. That one I can see pretty easily. This one is 5 here, 4 here, and then 4 here. So this one, the numbers changed. So is it linear? Is it going to form a line? No, not linear, because we can just set up, usually that's the right-hand column over the left-hand column. So 5 over 5 does not equal 4 over 5. There's no constant rate of change. Letter B, we're given a graph. Now if I had a ruler, I could try and see if I could make a line. I'll just use this I have who has card. So if I can connect all of these and it forms a straight line, if I can go through all points of the straight line, then it's linear. So I went through all 3 dots, so that says it's linear because it's a line, Or we can check our numbers. So it goes from 80 to 60, so that drops 20. From 60 to 40, that drops 20. And then this one, if we pretend there's a dot here, it drops from 40 to, oh, well, we can't actually see that because it's a little zigzag thing. So we can use these ones, and it goes over 2 boxes, which is actually 8. Then it goes over 8 again, and it would go 8. So because these numbers are the same, we know that it has a constant rate of change. So we'll say it's a line, and the constant rate of change is negative 20 over 8, which equals negative, take a 4 out, 5 over 2. So it drops 5 minutes for every volunteer. So maybe the work that needs to be done, the workload, the time spent doing the work decreases for volunteers that are added. So now we're talking about not just linear, but proportional. Proportional. 2 quantities have a proportional linear relationship if they have a constant ratio and a constant rate of change. So they have what we just did. They make a line. And then it says, so I wrote some little hints here. To be proportional, the relationship must have a constant rate of change, or it must be a line, which we just did, the outside ratios. And it needs to go through the origin. So to check to see if it goes through the origin, we check the inside ratios, or we can look at the graph. So the inside and the outside ratios have to be constant in order to be proportional. So we have to check 2 things in these next problems. So on slide 6, it says use a table to determine if there's a proportional linear relationship. So proportional, we need a constant rate of change and a CR, constant ratio. So basically we're going to check outside and inside ratios between a temperature in degrees Fahrenheit and a temperature in degrees Celsius. Explain your reasoning. So a couple different options here. So we're going to make our crocodile bumps. So this crocodile bumps tells me if it's going to be a line or not. So it goes out by 5, 5, 5, 8, nope, 9, sorry. 9, 9, 9, 9. So is it linear? Yes. And it says degrees Fahrenheit first. So the constant rate of change is 9/5 inside. So we need to divide the numbers. Not starting at the origin because, well, we can. We need to make sure that 32 over 0 is equal to 41 over 5, which is equal to 50 over 10. So we can probably stop here. This is 0. If it's not 0, 0, it doesn't go through the origin, so we're automatically knowing it's not proportional. We could also say that these are not equal, so the inside ratios, this says does not go through the origin, and therefore, is this asking us if it's proportional? To figure out if it's proportional. So this is good, this is no good. So this is together, this means that this relationship is not proportional. Not prop, I'm going to abbreviate. So there's a graph, our table. Here's a graph. We can do to check the same thing. So outside linear, is it a line? Is that a line? Yes, it's a line. So we're good there. Inside means we are going to check, because you can't really see the inside ratios, we're just going to divide the y coordinate by the x coordinate. And if those aren't equal for all of them, then we have a not proportional. So these happen to be the same numbers, because tricky, it's the graph that goes along with the top one. So yes, it's a line. No, it's not. Does not go through the origin. So not through origin. Therefore, this relationship is not proportional. Okay, one more. Use a table to determine if there is a proportional linear relationship between the mass of an object in kilograms and the weight of the object in pounds. So honestly, a better word right here would be origin, because the inside ratios double check that we go through the origin. Okay, so outside, crocodile bumps. 20 to 40, 40 to 60, 60 to 80 is all 20. 9 to 18, these are all multiples of 9, so this is 9s. And it tells us the mass in kilograms over the weight in pounds. So the mass in kilograms, 9 over 20. So because these are all the same, it's linear, it has a constant rate of change. So good there. Inside, we need to divide all of the numbers to figure out if this goes through the origin, if those numbers are all the same. So 9/20ths, you could divide them. And I'm actually going to notice a pattern here. 18/40ths, well, that's going to simplify to 9/20ths. 27/60ths, that's going to simplify to 9/20ths. 36/80ths, that also simplifies to 9/20ths. So all of them are 9/20ths. Therefore, this goes through the origin. Goes through origin. Check. This relationship is proportional. There we have it. Have a great day.